Okay, I'm going to discuss today the difference in series RLCs versus parallel RLCs with respect to the way we draw the phasors for the two different circuits. Okay, so when we did series RLCs, we have series components, and of course I've drawn either this and this, or this and this as our two phasors. When we drew our series RLCs, our resistive voltage drop was always on the horizontal, right? Because and that's never going to change. The current through the resistive portion is always going to be directly in phase with the voltage. Um, so that portion is always going to be on the horizontal. However, when we did series circuits, we drew our inductive voltage drop, or our inductive reactance, our inductive VARs, whichever one it was we were working with. We always drew them in a positive direction, and the capacitive reactance, or the capacitive voltage drop, or the capacitive VARs was always drawn in a negative. Now, the reason being is the portion of the component in a series circuit that's always the same is our current. And we were dealing with voltage drops, right? So our voltage drop across an inductor and a resistor in series was always going to be up here, right? Voltage was going to happen first, and then the current was going to lag behind the voltage. If we had had a resistor and a capacitor in series, our voltage drop is going to be down here. Impedance, whichever one we were using, was always going to be down here, because in a capacitive circuit with overall capacitance, the current happens first and then the voltage, right? Current leads the voltage. This hits its peak, later on this hits. Okay? Now, when we connect these same devices in parallel, we change the way they're drawn. And the reason being is that our current across our resistor is still going to be on the baseline, right? That, like I said earlier, that's never going to change. And that voltage is now what's going to be consistent, right? We're going to have the same voltage here as we've got here as we've got here, right? 120 volts is going to be seen across one of them. So, parallel circuits, we're always adding currents, right? If we had three resistors in parallel, and this had 2 amps, and this had 3 amps, and this had 4 amps, we just add them up together, and that would give us 9 amps of total current flow, right? We're going to do the same thing in parallel, only now we're going to add them vectorially, and because we're adding current in the inductive branch, when we're dealing with an inductor, they're always lagging, right? The current is behind the voltage. So now, because our voltage is our baseline, the current's drawn as a negative value, right? This is the purely inductive current right here, and this would be the net current if there was a resistor and inductor in series in that branch. Okay, so our inductive current is drawn in a negative value because the current is behind the voltage, right? And in the capacitive branch, the current is drawn this way because now our current needs to lead the voltage, right? It's a capacitive circuit. The current's going to hit its peak before the voltage does, right? So a capacitive current is drawn as a positive, and an inductive current is drawn as a negative, whereas an inductive voltage drop is drawn as a positive, and a capacitive voltage drop is drawn as a negative in a series circuit. But remember, all we are doing is we're just shifting, here our current is our reference, here the current is the resultant, and our voltage is capacitive. We're going to move it up, this will move it down, our voltage is going to be our horizontal or our baseline. Okay? So that's why the phasors are drawn differently in a series circuit as opposed to a parallel circuit.